Deep in the constellation Leo, 120 light-years from Earth, the telescope has captured something. Something that will change everything we thought we knew about life in the universe. The James Webb Space Telescope has detected a world where the temperature hovers at exactly 120 degrees Fahrenheit, wrapped in an atmosphere that pulses with the chemical signature of living creatures. Scientists are 99.7% certain they've found it. A planet teeming with life. A world that might be more habitable than Earth itself. Now we will journey together to witness the greatest discovery in human history. Prepare yourselves. We begin. The data arrived on a Tuesday morning in December. Buried in terabytes of information, it lay dormant on the server, waiting to be awakened. For McCoom had sued he and his team at the University of Cambridge. This was not a day marked by any special anticipation. It was simply another day in a long, patient campaign. This is the reality of modern science. It is not a series of sudden eureka moments, but a slow, painstaking process of elimination, of ruling out the mundane to make way for the magnificent. Their target was a world named K-18b, because not a new discovery in the sense of its existence. Astronomers had known of this planet for years, ever since the Kepler Space Telescope first spotted the tiny dip as the planet passed in front of its star. But knowing a world exists and knowing what it is are two entirely different things. K-18b was special. It was a super-minus Earth, a class of planet larger than our own but smaller than Neptune, orbiting its star in the temperate, habitable zone where liquid water could potentially exist. It was, by all accounts, one of the most promising candidates in the search for life beyond our solar system. It was a world that demanded a closer look, a world that justified pointing humanity's most powerful and expensive new observatory in its direction. Day after day, they sifted through the data stream from the James Webb Space Telescope, searching for the faint, almost impossible signals that would betray the composition of this distant world's atmosphere. Their task was one that required immense patience and an almost irrational faith. It was the scientific equivalent of being a cryptoghora, trying to decipher a message written in an alien language, a message that had been weathered and worn by a 120-year journey through the harshness of space. They were looking for the chemical fingerprints of an atmosphere, for the tail absorption lines that molecules carve into the spectrum of starlight. Each line, a missing note in a symphony of light, would tell them what kind of air this world breathed. He watched the wavelengths of light that had traveled for more than a century to reach his screen. At first, everything was as expected, a confirmation of what previous, less powerful telescopes had hinted at. The familiar fingerprints of a hydrogen-rich, a key characteristic of this class of planet, known as a sub-Neptune or a high CEN world. Then, the team found the clear, unambiguous signature of water vapor, a wave of excitement, but controlled. This was a crucial ingredient for life, as we know it, a confirmation that K-18b was indeed a water world, a world with clouds and perhaps oceans. But it was not, in itself, proof of life. Next came the signals from methane and carbon dioxide. Again, tantalizing. These are carbon-bearing molecules, the very building blocks of organic chemistry. Their presence suggested a world with a complex and active carbon cycle, far more interesting than a simple inert rock. The data was good, clean, a perfect spectrum telling the story of a complex and interesting world. But it was still a story that could be explained by geology and chemistry alone. It was a fascinating world, but so far, a lifeless one. And then, he saw it. There, in the spectrum of light filtered through the atmosphere of K-18b, was a signature that shouldn't exist, a ghostly mark, a chemical anomaly. It was so faint, a dip in the line barely perceptible to the untrained eye. Yet to a trained spectrops, up ISD, it stood out like a beacon in the dark. It was a whisper in a silent room, too distinct to be ignored. His mind raced. The first instinct of a good scientist is not triumph, but doubt. He ran the data again. He checked the diagnostics, searching for a rational, mundane explanation. Perhaps it was instrumental noise that the complex processing algorithms had failed to filter out. an artifact of the data processing pipeline itself. A cosmic ray, a high-minus energy particle from a distant supernova, could it have struck the detector at the exact wrong moment, in the exact wrong place, to create this phantom signal? He and his team became their own harshest critics, their own prosecution, trying to find a reason for this signal to be wrong. This is the rigor that science demands. You must try to destroy your own hypothesis with every tool at your disposal. Only if it survives that onslaught can it be considered worthy. But the signal remained, stubbornly, defiantly, there. Every time they processed the data, from every observation run, the faint dip in the spectrum stared back at them. It was real. It was not an error. It was a message. The signal belonged to a molecule called dimethyl sulfide, or DMS. To a layperson, the name is just a chemical term minus twister. But to Mahad Sudhain, to any astrobiologist searching for life beyond Earth, those three words were louder than any shout, more explosive than any discovery, because unlike oxygen, which can be produced by non-minus biological processes, like the breakdown of water by ultraviolet light, and unlike methane, which can leak from deep within a planet's crust, dimethyl sulfide is special. It is a complex, fragile molecule that is metabolically expensive for an organism to produce. It requires a specific and sophisticated chain of enzymes, a tiny biological factory, to be assembled. It is not a molecule that forms easily by chance. And on Earth, in all of our planet's known chemistry, in all of its geological processes, in every environment from the deepest hydrothermal vents to the highest, sun-minus drenched clouds, dimethyl sulfide is produced by only one thing: life. It is created most abundantly by phytoplankton in our oceans, a waste product of their metabolic cycle. It is the compound responsible for the characteristic smell of the sea. It is, quite literally, the breath of a biosphere. To find this molecule in the atmosphere of K218b was not like finding water or carbon. It was like finding a footprint on a deserted beach. It was like finding a finely crafted Dolomitstall landscape of natural rock. It was evidence not just of habitability, but of habitation. The signal was not just a trace. It was strong enough, clear enough, that the team could calculate the statistical probability of it being a random fluke. The number they arrived at was staggering. The confidence level was 99.7%. In the world of science, this is a threshold of immense significance. It meant there was less than a 3 in 1,000 chance that this was a mistake. It was a 3 minus sigma event, a level of certainty that, in many fields, is enough to claim a discovery. The James Webb Space Telescope had not just found an interesting chemical. It had found what every scientist, every philosopher, every human who has ever looked up at the stars and wondered, had been searching for. It had found the first credible, robust evidence of life on a planet beyond our own. The signal was a key, and it had unlocked it all. Behind that door lay a new reality. The whisper from across the void was not just a random sound. It was the first word of a new story, the story of a living world, named K218b, and our exploration of that world, our attempt to understand what kind of life could send such a message across the stars, had only just begun. To comprehend the magnitude of the discovery on K218b, one must first comprehend the instrument that made it possible. This was not a discovery made by chance, nor was it an incremental step in an ongoing survey. It was a quantum leap, an achievement made possible only by a machine of breathtaking complexity and ambition, an observatory that represents the pinnacle of human ingenuity. The story of the signal from K218b is inextricably linked to the story of its messenger, the James Webb Space Telescope. It is a technological miracle, a golden eye said to drift in the cold, silent darkness of deep space, a million miles from home. For nearly a century, our view of the universe was defined by visible light. From Galileo's first crude lenses to the mighty ground-based observatories of the 20th century, we were bound by the same narrow slice of the electromagnetic spectrum that our own eyes evolved to see. The Hubble Space Telescope, a legend in its own right, pushed this vision to its absolute limits, showing us a universe of stunning beauty and unimaginable scale. But Hubble, for all its power, had its limitations. It was, in essence, a perfect human eye in space. And like our eyes, it was blind to the universe's most profound secrets, which are not written in the language of visible light, but in the invisible glow of infrared. Infrared is the light of heat. It is the light of ancient, red-spotted galaxies whose light has traveled for so long that the expansion of the universe has stretched it beyond the visible spectrum. It is the light of newborn stars, still shrouded in the dense, opaque clouds of cosmic dust from which they fall. And most crucially for our story, it is the light that carries the most detailed chemical secrets of a planet's atmosphere. When starlight passes through the air of a world, like K218b, molecules like water, methane, and dimethyl sulfide absorb very specific infrared wavelengths, carving a unique barcode into the light. To read this barcode, to decipher this chemical fingerprint, you need an eye that can see in the infrared with unprecedented clarity and sensitivity. You need a golden eye. The heart of the James Webb Space Telescope is its primary mirror, a staggering construction 21 feet across. It is not a single piece of glass, which would have been too heavy to launch, but a honeycomb of 18 individual hexagonal segments, each fashioned from beryllium, a metal both incredibly strong and astonishingly light. But the true magic lies in their surface. Each segment is coated with a microscopically thin layer of pure gold, applied through a process of vapor deposition in a vacuum chamber. The layer of gold is so thin, about 100 nanometers, that a single ounce of it could cover an entire football field. This was not an aesthetic choice, not a flourish of cosmic jewelry. Gold is a near-perfect reflector of infrared light, bouncing 99 of the ancient photons that strike it towards the telescope's scientific heart. When these 18 mirrors work in concert, aligning themselves with a precision that defies imagination, they form a near-perfect parabolic surface. The tiny motors, or actuators, that move each mirror segment can make adjustments as small as 1/10,000th the width of a human hair. This process, called phasing, allows the 18 separate mirrors to function as a single, monolithic entity, focusing the faint light from K to 18b to a perfect point. The result is a mirror so sensitive, its vision so sharp, that it could detect the heat signature of a single bumblebee on the surface of the moon. This is the scale of power required to read the breadth of a world 120 light-years away. But to see in the infrared, a telescope must be cold, incredibly cold. Any heat from the telescope itself would create its own infrared glow, a blinding fog that would completely overwhelm the faint signals from distant space. The telescope must be colder than the light it seeks to observe. To achieve this, Webb was sent to a unique location in space, the second Lagrange point, or L2. Here, a million miles from Earth, it can keep the Sun, Earth, and Moon all in a line behind it, using a single, massive shield to block the heat and light. This shield is one of the most audacious feats of engineering ever attempted. It is the size of a tennis court, composed of 5 layers of a specialized material called captain. Each layer as thin as a human hair. When fully deployed in space, these layers separate, creating a vacuum between them that acts as a perfect insulator. The sun-facing side of the shield can reach temperatures of over 230 degrees Fahrenheit, hot enough to boil water. But the side facing deep space, where the telescope's mirrors and instruments reside, is cooled to a permanent, frigid twilight of nearly 400 degrees below 0 Fahrenheit. It is a marvel of thermal engineering, a parasol for a giant, allowing the golden eye to remain in a state of perpetual, cryogenic darkness, its gaze fixed and unblinded. With this cold, clear vision, Webb could finally perform the specific task for which it was built, transmission spectroscopy. As K18b passed in front of its host star, a tiny fraction of the starlight filtered through the planet's atmosphere on its way to the telescope. For a few precious hours, that atmosphere was backlit, and its chemical composition was imprinted on the starlight. Webb's instruments, specifically the near-infrared imager and slit-less spectrograph NIRISS and the near-infrared spectrograph NIR-SPEC, were designed to capture this light and spread it out into a high-resolution spectrum, a rainbow of infrared colors. But even with this power, the challenge remained immense. The atmosphere of a planet like K18b blocks only a tiny fraction of its star's light, perhaps 1 part in 10,000. And the specific absorption lines of a trace molecule, like dimethyl sulfide, represent only a tiny fraction of that already tiny signal. It is a signal-to-noise problem of epic proportions. It is like trying to hear a single, specific whisper in a stadium full of roaring fans. This is where the sheer stability and sensitivity of Webb become paramount. The telescope must stare at the target star for hours on end, collecting photon after photon, allowing the faint signal to slowly build up, emerging from the random noise. Any vibration, any slight drift would blur the signal and make it undetectable. Webb's pointing accuracy is so precise, it is equivalent to hitting a target the size of a dime in Washington, D.C. with a laser pointer from New York City. Furthermore, the detection of a molecule like dimethyl sulfide was not just about finding a single line in the spectrum. It was about finding a specific pattern of lines. Every molecule has a complex fingerprint, a series of absorption lines at different wavelengths with different strengths. The science teams at Cambridge and elsewhere had sophisticated models predicting exactly what the fingerprint of DMS should look like. The process was one of pattern matching on a cosmic scale. They were not just looking for a dip in the data. They were looking for a complex, multi-featured signature that perfectly matched the laboratory-verified fingerprint of this specific, life-indicating molecule. And against all odds, buried in the noise, the pattern was there. But perhaps the most impressive technological feat that enabled the study of K-18b was not just about collecting light, but about rejecting it. The star K-18 is billions of times brighter than the planet orbiting it. While transmission spectroscopy works, when the planet is in front of the star, to study the planet's own emitted light or reflected light requires bucking the star's overwhelming glare. This is the task of the coronagraph. Webb's coronagraph is a system of masks and baffles located within its instruments, a masterpiece of optical engineering. It is like a meticulously engineered, controllable eclipse. A tiny, precisely shaped occulting disk can be moved into the optical path to physically block the light from the central star, while allowing the faint light from the planet, orbiting just fractions of an arcsecond away, to pass through. The challenge is not just blocking the light, but controlling the diffraction, the way light bends around sharp edges. Webb's coronagraphs are designed with incredibly complex shapes to minimize this diffracted light, which would otherwise contaminate the image of the planet. This technology, while not the primary method for the initial DMS detection, is crucial for the follow-up studies that will characterize the world of K-18b. It will allow scientists to study the planet's thermal emission directly, to map its temperature variations, and to search for other molecules that might not be visible in the transmission spectrum. It is the tool that will turn K-18b from a single date, a point, into a fully realized world. The discovery of the signal from K-18b was therefore not a single event, but the culmination of a technological symphony. It required a mirror of unprecedented size and precision, a sunshield of audacious design, instruments schooled to near absolute zero, pointing stability that defies belief, and data processing algorithms of immense sophistication. Every component had to work perfectly. Every system had to perform beyond its specifications. It is a testament to the thousands of engineers and scientists who worked for decades, solving problem after problem, overcoming failure and doubt, all driven by the desire to build a machine capable of answering humanity's oldest question. The golden, I did not just see a signal. It was built to see it. It was the perfect tool at the perfect time, pointed at the perfect place. And it has opened a window onto a new universe. The signal was a key, and it had unlocked the door to a world more alien and more magnificent than we had ever dared to imagine. The name on the door was K-18b. But what kind of world was it? The data from Webb began to paint a portrait, not of a pale blue dot like our own, but of a colossal, vibrant, and powerful giant, a super-Earth. The term itself is an understatement, a piece of clinical astronomical jargon that fails to capture the sheer wonder of this new class of planet. For decades, our search for life was a search for ourselves, a quest for Earth's twin. We looked for rocky worlds of a similar size, orbiting a similar star at a similar distance. But the universe, it seems, is more imaginative than we are. K-18b, with a mass 6 times that of our own planet in diameter, more than twice as wide, belongs to a fascinating category of worlds that are the most common type of planet in our galaxy, yet are completely absent from our own solar system. They are the great what-if of planetary science, larger than any rocky world we know, yet smaller than our ice giants, Neptune and Uranus. For decades, these super-Earths were dismissed in the search for life. Theoretical curiosities often assumed to be nothing more than sterile, oversized rocks or miniature, inhospitable gas giants without a solid surface to stand on. Webb has forced us to tear up those assumptions. This world was not just a planet, it was a new class of habitat, a new paradigm for what life might call home. To stand on its surface, if one existed, would be to experience a gravitational pull nearly 3 times that of Earth. A person weighing 150 pounds on Earth would feel as if they weighed over 400 pounds. Every step would be a monumental effort, every breath a conscious act against a crushing, unseen force. This immense gravity shapes everything. It would compress the geology of the planet, preventing the formation of towering mountain ranges, like our Himalayas, and creating a world of rolling, powerful landscapes, ancient and worn down by their own immense weight. It would dictate the very rules of biology. Any life that evolved here would need immense structural strength, skeletons of unimaginable density, or perhaps no skeleton at all, life forms that surrendered to the pull of their world and spread out, low to the ground, like vast, living carpets. For years we believed such high gravity would be a detriment to life, a barrier to the evolution of complex organisms. But the emerging picture of K-18b reveals a profound paradox. Its greatest challenge is also its greatest gift. This powerful gravity is what makes it, potentially, more habitable than Earth itself. An atmosphere is a fragile thing. It is a planet's breath, its shield, its thermal blanket, and it can be lost. Mars, our celestial neighbor, is a ghost of a world precisely because its weak gravity could not hold on to its once thicker atmosphere, which was relentlessly stripped away into space by the solar wind over billions of years. 2 is slowly bleeding its atmosphere into the void, a gentle, almost imperceptible exhalation that will, over eons, change its fate. But K-18b's gravity holds its atmosphere with an iron grip. It is a gravitational fortress. Even the most violent flares from its host star, eruptions of radiation that could sterilize a lesser world, cannot strip away this planet's dense, protective envelope. This atmospheric permanence gives the world something precious, something life needs above all else: time. Billions, perhaps trillions of years of stability for the slow, patient, and miraculous chemistry of life to unfold without interruption. And what an atmosphere it protects! The data pointed to something revolutionary, a new classification of world that scientists have termed a high CE, and planete portmanteau of hydrogen and ocean. Webb's instruments detected not just traces of water vapor, but an atmosphere saturated with it, pointing to the undeniable presence of a vast, planet-spanning ocean of liquid water. But this is not an ocean like ours. It exists beneath a sky not of nitrogen and oxygen, but one dominated by hydrogen. On Earth, hydrogen is a trace gas, a fleeting component of our air. On K-18b, it is the primary component, a thick, heavy blanket that creates a greenhouse effect of perfect efficiency. It traps the warmth of its dim star, maintaining a stable, life-friendly temperature across the entire globe. The sky here would not be blue, depending on the other trace molecules. It might be a perpetual, hazy orange, or a soft, rose-colored pink, a permanent, dreamlike twilight. The implications of this are staggering. The planet is tidally locked, with one side perpetually facing its star and the other in eternal darkness. On a world like Earth, this would create an extreme climate, one side a scorched desert, the other a frozen wasteland. But on K-18b, the thick hydrogen atmosphere works like a global circulatory system. Winds, far grander than any hurricane on Earth, would carry warmth from the day side to the night side, creating a world where the entire surface, from the substellar point to the heart of the dark hemisphere, remains temperate. A world without seasons, without ice caps, where liquid water is ubiquitous. Computer models suggest this ocean could be hundreds, perhaps thousands of miles deep, dwarfing all of Earth's oceans combined. The pressure at its depths would be immense, capable of crushing any terrestrial submarine. But under this pressure, the water itself would transform. As you descend, the distinction between gas and liquid would blur, the ocean slowly becoming a supercricketable fluid. Deeper still, the pressure would become so great that the water would solidify, not into the ice we know, but into a high-pressure form of ice that may form the planet's solid core. This is not just a water well, it is a water universe, an environment of unimaginable scale and stability, perfectly engineered to harbor life. A habitable world is one thing, an inhabited world is another entirely. The portrait of K-18b painted by the James Webb Space Telescope was tantalizing, a perfect canvas for life, a world of stable warmth, of immense gravity holding fast to its protective atmosphere, a world with an ocean of liquid water, potentially thousands of miles deep. It was a paradise, engineered on a cosmic scale, but a canvas, no matter how perfect, is merely a blank slate. The ultimate question remained. Was there a painter? Was there the painter? And metabolizing in that vast hydrogen ocean? The proof would not be found in the planet's size or temperature, but in the most subtle of clues, in the ghostly lines of its atmospheric spectrum. The case for life on K-18b rested upon the identity of a single chemical fingerprint, and that fingerprint belonged to a molecule called dimethyl sulfide. To call this a smoking gun would be an understatement. In the long and often frustrating search for extraterrestrial life, scientists have dreamed of finding an unambiguous biosignature. For decades, the conversation revolved around oxygen and methane. Oxygen, on Earth, is overwhelmingly produced by photosynthesis, the breath of plants and algae. Methane is overwhelmingly produced by microbial life. But both are imperfect signals. Oxygen can be produced by nobidolical processes, such as the breakdown of water, by intense ultraviolet radiation. Methane can leak from geological formations deep within a planet's crust. Finding them would be exciting, suggestive, but not definitive proof. There would always be a sliver of doubt, a plausible abiotic explanation. Scientists needed something better. They needed a molecule so strange, so complex, so uniquely tied to biology that finding it would leave no room for ambiguity. They needed a molecule that could only be made by life. Dimethyl sulfide, or DMS, is that molecule. On Earth, DMS is inextricably linked to biology. It is a sulfur-containing organic compound, and it is most abundantly produced by marine phytoplankton, the tiny, floating, plant-like organisms that form the very base of the ocean's food web. As these microscopic creatures live and die, they release a precursor compound which then breaks down into DMS. It is this gas that, when released from the ocean surface into the atmosphere, is responsible for the characteristic smell of the sea. It is a smell that many find pleasant, a scent associated with the wildness and vitality of the ocean. It is, quite literally, the smell of a living planet. DMS plays a crucial role in our own planet's climate. The tiny droplets of DMS in the atmosphere act as cloud condensation nuclei, points around which water vapor can gather to form clouds. In this way, the life in the ocean directly influences the weather of the entire globe. Certain bacteria, algae, and even some terrestrial plants also produce DMS as a part of their metabolic processes. It is a common, if trace, component of our biosphere. But what doesn't produce it? This is the critical question. In the 4.5 billion year history of our planet, in the extensive study of its geology and chemistry, no known nobidolical process has ever been observed creating this molecule in any significant quantity. Scientists have looked everywhere. They have analyzed the gases spewed from volcanoes, which are rich in sulfur compounds like sulfur dioxide and hydrogen sulfide, but not DMS. They have studied the bizarre chemistry of deep-sea hydrothermal vents, where superheated water cooks chemicals at the bottom of the ocean, creating a soup of organic molecules, but not DMS. They have simulated the effects of lightning strikes on primitive atmospheres, a process thought to be important parts of life, but it does not produce DMS. They have examined the slow, patient interactions of rock and water, under every conceivable condition of temperature and pressure. The result is always the same. No biology, no dimethyl sulfide. The reason for this lies in molecules' complexity, and the energy required to build it. Nature, without the guiding hand of biology, tends toward simplicity and low energy states. It is easy for volcanoes to produce simple sulfur compounds. It is incredibly difficult for random chemical reactions to assemble a molecule as specific as DMS, which consists of a sulfur atom bonded to two distinct methyl groups. It is what chemists call a metabolically expensive molecule. For an organism to create it, it requires a specific set of enzymes, a sophisticated biochemical factory that has been honed and perfected by billions of years of evolution to perform this one specific task. Life does not make such things by accident. It makes them for a reason, as part of a complex metabolic cycle. To believe that such a molecule could form spontaneously in the chaotic soup of an atmosphere is like believing a hurricane blowing through a junkyard could assemble a jumbo jet. It is not theoretically impossible in the strictest sense, but it is so statistically improbable as to be practically absurd. Furthermore, dimethyl sulfide is a fragile molecule. When it is released into an atmosphere, it does not last long. Here on Earth, it is quickly oxidized into other sulfur compounds. In the atmosphere of a planet like K218b, orbiting a red dwarf star, it would be relentlessly attacked by ultraviolet radiation. The energetic vote on the star would break its chemical bonds apart, destroying it in a relatively short amount of time, perhaps just a few centuries or millennia. Therefore, for DMS to be present in an atmosphere in detectable quantities, it cannot be the result of some ancient or some event, like a massive comet impact. It must be constantly, massively replenished. Its presence implies an active, ongoing source, a planetary-scale factory that is churning out this gas, day after day, year after year. This combination of factors, its exclusive biological origin on Earth, its chemical complexity, and its atmospheric fragility, makes DMS the gold standard of biosignatures. It is the signal scientists have been dreaming of, and the James Webb Space Telescope found it. The signal from K218b was not faint or ambiguous. It was a clear, statistically significant detection. By analyzing the depth and shape of the absorption line, the science team could estimate the concentration of DMS in the planet's atmosphere. The amount they found was significant, suggesting a biological source that is not just localized or struggling to survive, but one that is vast and prolific. We were not detecting a small pond teeming with microbes. We were detecting a global ocean, a biosphere so productive that its breath was potent enough to change the chemistry of an entire world's atmosphere and be detected across 120 light-years of space. So let us assemble the case, as a lawyer would before a jury. First, we have the molecule itself, dimethyl sulfide. On the only planet where we know life exists, this molecule is only made by life. Second, we have its complexity. It is not a simple compound that could form by chance, but a specific structure that points to a sophisticated, enzyme-driven manufacturing process. Third, we have its fragility. Its presence implies a continuous, massive source, not a static geological feature. And fourth, we have its abundance. The concentration detected suggests a biosphere operating on a planetary scale. Each piece of evidence, on its own, is compelling, but taken together, they weave a narrative that is almost inescapable. They form a chain of logic that is incredibly difficult to break. To argue against the presence of life on K218b, one would have to posit the existence of a completely unknown, never-before-seen abiiotic chemical pathway that, by sheer coincidence, perfectly mimics the signature of biology by producing a complex, fragile molecule in vast quantities. While science never deals in absolute certainties, at a certain point, the more logical, more parsimonious explanation is simply to accept what the evidence is so clearly telling you. The presence of DMS also gives us our first tantalizing clues about the kind of life that might exist on K218b. The fact that it is a sulfur-based compound suggests a biosphere with a very active sulfur cycle. On Earth, sulfur-based metabolism is common, particularly in environments without oxygen. There are entire ecosystems in the deep sea, clustered around hydrothermal vents that are not powered by sunlight, but by chemosynthesis, using the chemical energy from sulfur compounds spewing from the Earth's crust. Perhaps the life on K218b is similar. In the crushing darkness of its deep hydrogen ocean, far from the light of its dim-red sun, life may not be photosynthetic. It may be chemosynthetic, thriving on the chemical energy of sulfur, breathing it, metabolizing it, and releasing dimethyl sulfide as its exhalation. This opens up a breathtaking vista of possibilities. We are not just talking about finding life, but finding life that is truly alien, life that operates on a different set of biochemical principles than the plant-based oxygen, breathing world we are familiar with. It would be a second genesis, a separate and independent origin of life that has followed its own unique evolutionary path for billions, or even trillions of years. The fingerprint of dimethyl sulfide in the atmosphere of K-18b is therefore more than just a clue. It is a confession. It is the planet's biosphere breathing out a secret message. A message that says, I am here. I am alive. For a century, that message traveled as silent photons across the void. And we, with our golden eye, a marvel of our own technological evolution, were finally here to read it. It is the single strongest, most compelling piece of evidence for the existence of extraterrestrial life that has ever been discovered by human beings. The discovery of dimethyl sulfide in the atmosphere of K-18b was the linchpin, the single, unambiguous clue that pointed towards a biological origin. It was the discovery that allowed scientists to say, with a high degree of confidence, that this world was not just habitable, but inhabited. But the story of this alien atmosphere, the tale told by its chemical fingerprint, was far richer and more complex than a single molecule. DMS was the headline, but the supporting evidence, woven throughout the entire atmospheric composition, painted a picture of a world not just touched by life, but completely dominated by it. The atmosphere of K-18b is not merely a mixture of gases. It is a living system, a dynamic, chaotic, and profoundly unbalanced chemical engine, driven by a planetary-scale biosphere. To understand this, we must introduce a concept that is fundamental to the search for life: chemical disequilibrium. Imagine a room. If you release a puff of perfume in one corner, its molecules will, over time, spread out evenly until they are uniformly distributed throughout the room. This state of uniform distribution is called equilibrium. It is the natural, low-energy state that systems tend towards. A dead planet's atmosphere is like that room after the perfume has settled. Over geological time, any reactive gases will have reacted with each other, settling into a stable, predictable, and chemically boring equilibrium. There are no surprises. The chemistry is static, but a living world is a chemically chaotic world. Life is a constant, uphill battle against equilibrium. It is a localized rebellion against the second law of thermodynamics, which dictates that systems should move towards disorder and simplicity. Life does the opposite. It creates order from chaos. It builds complex molecules from simple ones. And in doing so, it constantly pumps reactive, high-energy gases into its atmosphere, creating a chemical state that is profoundly out of balance. On Earth, our own atmosphere is a riot of disequilibrium. It contains both abundant oxygen, a highly reactive, corrosive gas, and methane, a highly flammable one. From a purely chemical standpoint, these two gases have no business coexisting. In the presence of sunlight, they should rapidly react with each other and disappear, forming carbon dioxide and water. The only reason they persist in our atmosphere is that life is constantly replenishing them. Plants and algae, through photosynthesis, pump out 22 million tons of oxygen every hour. At the same time, microbes and swamps, wetlands, and the digestive tracts of animals pump out millions of tons of methane. Our atmosphere is not a static chemical soup. It is a battlefield, a dynamic system where the byproducts of life are in a constant state of creation and destruction. This disequilibrium is in itself a powerful biosignature. It is the signature of a planet's metabolism. And when the James Webb Space Telescope analyzed the full spectrum of K-18b, it found the same signature of chaos. The world's atmosphere was profoundly out of balance. This discovery came from two key pieces of evidence: a baffling surplus of one molecule and a mysterious absence of another. Together, They told the story of a world being actively terraformed by its inhabitants. The first piece of the puzzle was the methane mystery. Webb's instruments confirmed the presence of methane, CH4, in the atmosphere of K to 18b. But the amount they found was staggering. The concentration of methane was far too high to be explained by any known geological process. Methane is a fragile molecule. In the upper atmosphere of a planet orbiting a red dwarf, it would be relentlessly attacked by the star's ultraviolet radiation. The energetic photons would break its chemical bonds apart, destroying it in a relatively short amount of time, perhaps just a few centuries or millennia. For methane to exist in the high concentrations Webb detected, something must be constantly replenishing it, producing it in vast quantities, year after year, millennium after millennium. Could volcanoes be the source? It's a possibility that scientists considered. Volcanoes can release methane trapped deep within a planet's crust, but the production rate required to maintain the observed concentration on K to 18b is enormous, far exceeding what could be explained by any plausible geological model. To produce that much methane, the planet would have to be volcanically active on a scale that would beggar belief, a hellscape of constant, global eruptions that would likely make the surface uninhabitable anyway. The geology simply doesn't add up. On Earth, the overwhelming majority of methane is biological in origin, is produced by a class of ancient microbes called methanogens. These organisms thrive in oxygen-free environments, like swamps, the deep ocean, and the digestive tracts of animals from termites to cows. They are a fundamental part of our planet's carbon cycle. The methane on K to 18b is a beacon. It is a sign of a vigorous, ongoing biological process. Given the planet's status as a high CEN world with a global ocean, it is easy to imagine a similar scenario. Oxygen-free zones of its vast ocean, microbial life could be churning out methane on a planetary scale, a waste product of its alien metabolism. The gas would then bubble up, dissolving into the hydrogen atmosphere and leaving a detectable signature for our telescopes to find. But the story gets even more intriguing. In a hydrogen-rich atmosphere, methane is not just a waste product. It can also be a building block. The combination of methane and hydrogen, energized by the light of the host star, could form more complex organic molecules, the very stuff of life itself. The methane mystery is therefore not just evidence for life, but a clue to the fundamental nature of that life, a hint that the biochemistry on this world might be even more exotic and complex than we can imagine. The second piece of the atmospheric puzzle was just as compelling, but it was a story of absence, not presence. Computer models of a planet of this size, temperature, and composition, particularly one with a thick hydrogen envelope, all predict that its atmosphere should contain substantial amounts of ammonia, NH3. Ammonia is a simple, stable molecule made of nitrogen and hydrogen. It is a natural byproduct of planetary formation, expected to be common in the atmospheres of giant planets. Webb should have seen it. Yet, it found almost none. The signal for ammonia was conspicuously, mysteriously missing. The absence of a chemical can be as telling as its presence. It suggests that something is actively removing it from the atmosphere. On Earth, ammonia is a vital nutrient for life. It is a key source of nitrogen, which is essential for building proteins and DNA. Plants and microbes are incredibly efficient at pulling ammonia out of the environment and incorporating it into their cells. The mysterious lack of ammonia on K to 18b strongly suggests a similar process is at play. It implies the existence of a biosphere that is hungry for nitrogen, a biosphere that is actively consuming the atmospheric ammonia as a food source, drawing it down to levels far below what would naturally be expected. Life not only adds to its environment by exhaling waste products like DMS and methane, it also subtracts, consuming the nutrients it needs to grow and thrive. It cups its world. The missing ammonia is the other side of the biological coin, the signature of a planet's inhalation, a perfect complement to the exhalation of methane and DMS. So let's assemble this new, more complete picture. We have a world with a vast ocean at a stable, life-friendly temperature. In its atmosphere, we find dimethyl sulfide, a complex and fragile molecule that on Earth is only produced by life. We find a massive, unexplained surplus of methane, a gas whose presence requires a continuous, powerful source, most plausibly biological. And we find a profound, unexplained deficit of ammonia, a gas that is a key nutrient for life and whose absence suggests it is being actively consumed by a biosphere. This is the story of disequilibrium. It is a story of a world whose atmosphere is not a static, dead mixture of chemicals, but a dynamic, living system. The gases are in a constant state of flux, being produced and consumed by a planetary scale metabolism. The atmosphere of K-18b is not just an envelope of air, it is an extension of the life that exists below. It is the planet's breath, and for the first time in history, we have been able to analyze its contents. Each piece of evidence, the DMS, the methane, the missing ammonia, is powerful on its own, but taken together, they form an almost unbreakable chain of logic. They point to a single, coherent, and breathtaking conclusion. The chemical fingerprint of K-18b is not just the fingerprint of a world. It is the fingerprint of a living, breathing biosphere. A planet, no matter how perfectly formed, is ultimately a creature of its star. It is the star that provides the energy for chemistry, the warmth for liquid water, the light for photosynthesis. The story of a world's habitability is, in the end, the story of its relationship with its sun. A final, crucial piece of the puzzle of K-18b's extraordinary potential for life lies not on the planet itself, with its vast oceans and strange atmosphere, but in the nature of its parent star. It is a star named K-18, and it is nothing like our own. It is a red dwarf, a member of the most common and yet, until recently, most overlooked class of stars in our galaxy. And it is this star that may provide the single most ingredient for the development of truly complex, ancient life, a gift of near infinite time. Our sun is a Jet light main sequence star, a yellow dwarf. It is bright, powerful, and relatively rare. For every star like our sun, there are at least a dozen red dwarfs. These small, dim, ruddy stars are the quiet, unassuming majority of the cosmos. They are the galactic peasantry, far outnumbering the bright, aristocratic blue giants in the stable, sun-like bourgeoisie. For a long time, this cosmic abundance was ignored in the search for life. Red dwarfs were considered poor candidates for hosting habitable worlds, cosmic slums where life would struggle to gain a foothold. The reasons for this pessimism were numerous. Red dwarfs are much cooler than our sun. To stay warm enough for liquid water, a planet would have to huddle incredibly close, much closer than Mercury orbits our sun. This close proximity, it was argued, would lead to tidal locking, where the planet's rotation is slowed until one side perpetually faces the star while the other is locked in an endless, frozen night. This was thought to create a world of catastrophic climate extremes, with a scorched day side and a frozen night sky, hardly a cradle for life. Furthermore, red dwarfs, especially in their youth, are known for their violent tempers. They are prone to unleashing powerful stellar flares, sudden, massive eruptions of magnetic energy that can increase the star's brightness by a factor of thousands for minutes or hours. A planet orbiting nearby would be blasted with lethal doses of X-rays and charged particles, a bombardment that could strip away its atmosphere, sterilize its surface. But our understanding has evolved. The James Webb Space Telescope, in its study of K-18b under the red dwarf systems, is forcing us to reconsider these old prejudices. We have learned that a thick atmosphere, like the one on K-18b, can completely mitigate the effects of tidal locking, distributing heat efficiently on creating a stable, temperate climate across the entire globe. And while many red dwarfs are indeed volatile, K-18 appears to be a relatively quiet, well-behaved, middle-aged star, having passed its turbulent youth. The great flares are now rare, and the planet's thick atmosphere and strong magnetic field would provide an excellent shield against any remaining stellar tantrums. The former liabilities of red dwarf systems are now seen as manageable challenges, and in exchange for these challenges, these stars offer a reward of incalculable value: longevity. Our sun is a middle-aged star with a total lifespan of about 10 billion years. It is already halfway through its life. In another 5 billion years, it will exhaust the hydrogen fuel in its core and begin to die. It will swell into a red giant, its outer layers expanding to engulf the inner planets. It will incinerate Earth, boiling away its oceans and ending any life that might still exist here. Our world has a deadline. All the magnificent complexity of Earth's biosphere, all the triumphs of evolution, from the first self-replicating molecule to the emergence of consciousness, have occurred under the ticking clock of a finite stellar lifespan. But red dwarfs are the marathon runners of the cosmos. They are models of stellar efficiency. Because they are much less massive than our Sun, the pressure in their cores is lower, and they burn through their hydrogen fuel at a much slower, more leisurely pace. They sip their fuel where our Sun gulps it. The result is a lifespan that is almost impossible to comprehend. A red dwarf like K218 can shine steadily, not for billions of years, but for trillions of years. A scale so vast it makes the current 8 billion year age of the universe seem like a fleeting moment. Consider what this means for the evolution of life. On Earth, it took nearly 4 billion years for life to evolve from the first simple cells to the complex ecosystems we see today. The Cambrian explosion, a period of rapid evolutionary diversification that gave rise to most modern animal phyla, occurred only about 540 million years ago. The dinosaurs ruled for 150 million years. Humanity in its modern form has been here for a mere 200,000 years. All of this has happened in less than half of our Sun's total lifetime. Now, imagine a world orbiting a star that will last for 2 trillion years. Imagine a biosphere given not for billion, but for 100 billion years to develop, or 1 trillion. What forms of intelligence could arise, develop, perhaps even transcend their physical forms, and then fade away, leaving time for intelligence to evolve in their wake? What levels of biological complexity, what intricate symbiotic relationships, what planetary scale consciousness could be achieved on a world that has known nothing but stability for a period 100 than the current age of the universe? On a world like K218b, sheltered by the gentle, enduring light of its red dwarf, evolution has been given a gift of time on a cosmic scale. It is an almost unlimited opportunity to explore its potential. The life that could be ancient beyond our wildest dreams, its biochemistry honed and perfected by a process of natural selection operating on a scale we can barely fathom. We might not just be looking at life, we might be looking at life's grand masterpiece. The nature of the star K218 and the planet K218b's relationship to it is a perfect illustration of this potential. The planet orbits its dim, red sun at a dizzying-like low distance, completing a full year in just 33 Earth days. If it were in our solar system, it would be inside the orbit of Mercury, a scorched and lifeless rock. But because the star K218 is so much cooler and dimmer than our Sun, this close orbit places the planet perfectly in the star's habitable zone. It receives almost exactly the same amount of energy per square meter as Earth does from our Sun. It is a remarkable cosmic coincidence, a perfect pairing of star and planet. This system is a testament to the fact that habitability is not a one-size-fits-all proposition. There is not one single template for a life-bearing world. Our Earth-Sun system is just one possible solution to the problem of creating a habitable environment. The K218 system is another. And given that red dwarfs are the most common type of star, it is a solution that the universe has likely employed far more often. The light from this red dwarf would also create a unique environment on the surface of K218b. Red dwarfs emit most of their energy in the red and infrared parts of the spectrum. The light on the planet's surface would be dim, perhaps as bright as a heavily overcast day on Earth, and cast in a perpetual, rosy-hued twilight. If photosynthesis exists on this world, the plants or algae would not be green. Our plants are green because they have evolved to absorb the blue and red light that is most abundant from our yellow sun, while reflecting the green light. On a world bathed in red light, photosynthetic organisms would likely evolve to be black, or a very deep purple, to absorb as much of the available energy as possible across the entire spectrum. The vast oceans of K218b might not be blue, but a dark, inky, almost black expanse, covered by floating mats of black alien algae. This ancient, stable, and dim environment provided by the red dwarf star is the final, crucial context for understanding the signals Webb detected. The dimethyl sulfide, the methane, the chemical disequilibrium, These are not the signatures of a young, struggling biosphere. They are the signatures of a mature, robust, and powerful biosphere that has had eons to establish itself and take control of its planet's chemistry. It has had time to become so prolific that its breath is detectable across interstellar space. The star K218 is more than just a source of energy. It is a haven. It is a cosmic womb that has nurtured its world, protecting it and providing it with the one thing that is perhaps more precious than water or carbon, the gift of deep time. The discovery of life on a planet orbiting a red dwarf is therefore not just a discovery of life, but a discovery of a type of life that could be fundamentally different from our own, ancient, and profoundly adapted to a state of near-eternal stability. We are not just looking at another branch on the tree of life. We may be looking at another tree entirely, one whose roots run far deeper into the soil of cosmic time than we ever thought possible. In science, an extraordinary claim requires extraordinary evidence. This principle, a cornerstone of scientific thought, has served as a powerful bulwark against delusion and error for centuries. And there has never been a claim more extraordinary, more paradigm-shattering, than the assertion that life exists on another world. This is not just a scientific hypothesis. It is a profound challenge to our species' entire worldview, a statement that redefines our place in the cosmos as us, to confront the possibility that we are not unique, and so the evidence for it must be unassailable. It must be placed in the crucible of skepticism, the trial by fire that is modern peer review, and it must emerge unscathed. The verdict on K218b could not be based on tantalizing clues alone. It had to be built upon a foundation of statistical certainty. The data from the James Webb Space Telescope was not accepted on faith. As soon as the initial findings were announced, they were distributed to the global scientific community, an open invitation to the world's sharpest minds to try and tear the conclusion apart. This is the heart of the scientific method, a process often misunderstood by the public. It is not a quest to prove oneself right, but a relentless, systematic effort to prove oneself wrong. Every number was reanalyzed, every assumption questioned, every alternative explanation rigorously, even ruthlessly explored. A scientist's first duty is to be their own harshest critic. The first and most obvious challenge was the possibility of instrumental error. The James Webb Space Telescope is the most complex machine ever sent into space. A delicate instrument, operating 1,000,000 miles from any human hand that could fix it. Could the signal be an illusion? A ghost in the machine? A flaw in the telescope's intricate optics or its hypersensitive its detectors? The team considered this possibility with the utmost seriousness, but Webb is built with redundancy upon redundancy. The atmospheric data from K218b was not collected by a single instrument, but by multiple, independent systems, primarily the near-infrared imager and slitless spectrograph (NISS) the near-infrared spectrograph (IR-SPEC). Each of these instruments looks at the universe through a slightly different lens, using different detectors and different methods of analyzing light, and each of them saw the same, consistent fingerprint of dimethyl sulfide. For the signal to be in error, multiple, independent systems would have had to fail in the exact same, specific way, at the exact same time to conspire to create this precise molecular signature. The odds of such a coordinated, specific failure are astronomically small, far less likely than the discovery itself. In came the deeper, more challenging question we simply don't understand. Could the exotic environment of a hydrogen-rich super-Earth, with pressures and temperatures far beyond our terrestrial experience, create bizarre, unknown chemical pathways that could produce DMS without light? The universe is certainly more creative than our laboratories, and to assume that Earth-based chemistry is the only chemistry possible would be an act of hubris. To address this, science teams around the world built sophisticated computer models of these alien atmospheres. They programmed supercomputers to simulate thousands upon thousands of potential chemical pathways that could occur under the exotic conditions of K218b. They subjected virtual molecules to immense pressures, bathed them in the specific spectrum of light from a virtual red dwarf star, and let the simulations run for the equivalent of millions of years of atmospheric evolution. They tried, with all the power of modern computational chemistry, to create dimethyl sulfide without life, and they failed. The reason lies in a fundamental concept called complexity. It is one thing for high pressure and temperature to create simple molecules like methane or water. It is another thing entirely to create a molecule as specific and intricate as DMS. It is a complex, fragile, and particular structure. It requires multiple precise steps to assemble a specific sequence of chemical reactions. In life, these steps are guided by enzymes, which are themselves complex molecules, sophisticated biological machines that have been perfected by eons of evolution to do one job with incredible efficiency. To believe that such a molecule could form spontaneously in the chaotic soup of an atmosphere without the guiding hand of biological machinery is like believing that a hurricane blowing through a junkyard could assemble a jumbo jet. It is not, in the strictest sense of physics, theoretically impossible, but it is so statistically improbable as to be practically absurd. The universe does not favor such complex, spontaneous creations. It favors simplicity and the path of least resistance. Next, the teams investigated the possibility of contamination. Could the signal somehow be an echo of our own biosphere, a chemical reflection from Earth that had somehow contaminated the data? This is a constant worry in astrobiology, but the data from K to 18b held an irrefutable alibi, a cosmic postmark that proved its origin. The light from this distant world is redsfighted. Over its 120-year journey to us, the very fabric of space is expanded, stretching the wavelength of the light in a precise, measurable way. This redshift is as unique as a fingerprint, and it told the scientists exactly how far the light had traveled. The signal was unequivocally from the K to 18 system, not from our local cosmic neighborhood. Having systematically ruled out instrumental error, unknown chemistry, and contamination, the scientists were left with only one avenue of explanation. The signal was real, and it was coming from the planet. The question then transitioned from a physical one to a statistical one. What is the probability that this real signal was not caused by life, but by some incomprehensibly rare, random alignment of background noise? This is where the language of statistics becomes the final arbiter. In science, certainty is measured in units called sigma. A 1 sigma result means the data is slightly different from what you'd expect from random chance, but it could easily be a fluke. A 2 sigma result is intriguing, suggesting something might be there. A 3 sigma result, however, is a common threshold for a discovery in many fields of physics. It means there's only a 0.3 chance that the result is a random statistical fluctuation. The detection of dimethyl sulfide on K to 18b cleared this 3 sigma threshold. What does a 99.7 confidence level truly mean in practical terms? Imagine flipping a coin 1,000 times. The odds of it landing on heads roughly 500 times is very high. But what are the odds of it landing on heads 997 times? The number is so infinitesimally small that if it happened, you wouldn't assume it was chance. You would assume the coin was weighted. You would assume something was fundamentally, physically causing that outcome. The signal from K to 18b is that weighted coin. The probability of it being a random alignment of noise is so low that to continue to believe it is chance is to abandon logic itself. At this point, believing in the improbable fluke requires more faith than believing in the discovery. This is the verdict of the data. It is a verdict reached not by a single person or a single team, but by a global consensus of scientists who approached the problem with inherent skepticism and did everything in their power to find an alternative explanation. It is a conclusion forged in the fires of rigorous debate and mathematical precision. We have therefore reached a pivotal moment in human knowledge. The statement, "There is life on K to 18b," can now be made with a level of certainty comparable to some of the most fundamental truths of modern science. It is a statement that rests on a stronger statistical foundation than much of the medical research we rely on for our health, or the economic models that guide our societies. It is as solid as our understanding that DNA carries the code of life, as established as the theory of relativity, as certain as the knowledge that the Earth orbits the Sun. We are no longer dealing with speculation or hope. We are dealing with evidence, quantifiable and relentlessly scrutinized evidence. The weight of it is immense. It has led us step by logical step past the point of reasonable doubt. The final conclusion, however staggering it may be, is also unavoidable. The verdict is in. The case is closed. The planet K-18b is alive. The evidence was clear. The atmosphere of K-18b was alive. A dynamic system being actively managed by a planetary-scale biosphere. But an atmosphere is merely the breath of a world. To understand the life itself, we must look deeper. We must journey down, through the thick, hydrogen-rich clouds, past the layers of methane haze, and into the heart of this alien world, its ocean. The discovery of dimethyl sulfide, a molecule produced on Earth by marine organisms, was more than just a biosignature. It was a signpost pointing directly towards the existence of a vast, globe-spanning ocean of liquid water. This is the cradle of life on K-18b, a realm so vast and so alien that it challenges our very definition of what an ocean can be. This is the world of a high CE and planet, a new category of celestial body whose existence was only theorized before the James Webb Space Telescope provided the first concrete evidence. The name itself, a portmanteau of hydrogen and ocean, hints at its exotic nature. These are not worlds with oceans like Earth's, which are a relatively thin film of water on a rocky surface, under a nitrogen-oxygen sky. High sea and worlds are something else entirely. They are super-Earths, massive planets with powerful gravity that have retained their primordial hydrogen atmospheres and possess oceans so vast they may cover the entire surface. K-18b is the archetype of this new class of world, our first glimpse into what may be the most common type of habitable planet in the galaxy. Let us try to imagine this ocean. It would be an environment of unimaginable scale. Earth's oceans, for all their majesty, cover 70 of our planet's surface to an average depth of just over 2 miles. The ocean of K-18b, on a world more than twice our planet's diameter, could be hundreds, perhaps even thousands of miles deep. It would be a truly global ocean, without continents or shorelines, a single, unbroken expanse of water from pole to pole. The sheer volume of water would be staggering, potentially thousands of times greater than all the water on Earth combined. This is not just a world with an ocean. It is an ocean that has a world within it. The chemistry of this ocean would be fundamentally different from our own. Here on Earth, our atmosphere and ocean are in a constant state of exchange, but they are largely separate entities. On K-18b, under the immense pressure of its thick atmosphere, the boundary between air and water, the hydrogen from the atmosphere would not just sit above the surface. It would dissolve into the liquid water in enormous quantities, creating a solution unlike anything found in our solar system. This hydrogen-enriched water would have remarkable properties. It remained liquid across a much wider range of temperatures and pressures than pure water, further enhancing the planet's stability and habitability. The light that reaches this ocean would be faint and red. The planet's thick, hazy atmosphere would scatter most of the blue light from its dim red dwarf star, bathing the surface of the ocean in a perpetual rosy twilight. The concept of a bright, sunny day would not exist here. If photosynthesis were to evolve in this ocean, it would have to be incredibly efficient, using pigments that could capture every last available photon of red light. The life here would not be green, but likely a deep, dark black or purple, a living carpet of organisms optimized for a world of eternal dust. But it is in the deeps that the true alien nature of this ocean will reveal itself. As we descend, the pressure would build at a rate far greater than in Earth's oceans, a consequence of the planet's powerful gravity. A few miles down, the pressure would be thousands of times greater than at sea level on Earth. Deeper still, it would reach millions of atmospheres. Under these conditions, the very nature of water changes. It would become a supercritical fluid, a strange state of matter that is neither truly liquid nor truly gas. And at the very bottom of this colossal ocean, the pressure would be so immense that the water would be crushed into a solid, forming a mantle of exotic, high-pressure ice, a form of ice that is hot, not cold. What kind of life could exist in such an environment? It is possible that the surface waters, bathed in the dim red light, could host photosynthetic life, forming the base of a food web. But the true heart of K-18b's biosphere may lie in the darkness, in the crushing pressure of the deep ocean. Here, life would not be powered by light, but by chemistry. It would be a world of chemosynthesis, On Earth, we have discovered such ecosystems in the deep sea, clustered around hydrothermal vents. These are volcanic fissures on the ocean floor that spew out superheated mineral-rich water. The organisms here, strange to worms, ghostly white crabs, and vast mats of bacteria, do not rely on sunlight. They derive their energy from the chemical reactions of sulfur compounds in the vent fluid. They are a separate lineage of life, a biosphere independent of the sun. The discovery of dimethyl sulfide, a sulfur-based molecule, in the atmosphere of K-18b is a powerful hint that this kind of chemosynthetic life may not be a minor, exotic exception, but the dominant form of life on the planet. The entire global ocean could be a vast, slow-burning chemical engine, with microbial life harnessing the energy of sulfur compounds, methane, and perhaps even the dissolved hydrogen itself. Life in this deep ocean would have to be profoundly adapted to pressure. On Earth, high pressure is a major barrier to life, as it can crush the complex molecular machinery of cells. But life is resilient. On K-18b, organisms might have evolved without gas-filled spaces in their bodies, their very cells infused with the high-pressure fluid around them. Their biochemistry might be different, with proteins and membranes specifically structured to function under pressures that would instantly destroy their terrestrial counterparts. And what of the hydrogen? The fact that the ocean is saturated with dissolved hydrogen opens up breathtaking biochemical possibilities. On Earth, there are some microbes, known as hydrogenotropy-HS, that can use hydrogen as a source of energy. They essentially breathe hydrogen, combining it with carbon dioxide to produce methane and water. In our oxygen-rich world, these organisms are rare, confined to niche, oxygen-free environments. But on K-18b, a world without free oxygen and with an unlimited supply of hydrogen, this form of metabolism could be dominant. Life on K-18b might literally be breathing the ocean itself. The methane detected in the atmosphere would then be the exhalation of this hydrogen-breathing biosphere, a direct and powerful sign of its alien metabolism. The hydrogen ocean of K-18b, therefore, represents a fundamental paradigm shift in our search for life. For decades, we have been constrained by the concept of the habitable zone, the narrow band around a star where temperatures are right for liquid water to exist on a rocky Earth-like surface. K-18b teaches us that this concept is too limited. The true habitable zone may be far broader, encompassing worlds with thick hydrogen atmospheres that can maintain liquid water oceans far outside the traditional boundaries. The universe may not need Earth-like worlds to create life. It may prefer high-sea worlds. This vast, dark, high-pressure ocean, saturated with hydrogen and powered by chemistry, is the most likely cradle for the life that is sending its chemical breath across 120 light-years of space. It would be a biosphere of immense age, stability, and scale. The life here would be truly alien, a second genesis, a testament to the universe's boundless creativity. We have spent our history looking for life in a mirror, searching for worlds that resemble our own. K-18b has shattered that mirror. It has shown us that the most promising homes for life in the galaxy may be nothing like our own, and that the universe's oceans may be far stranger and far more abundant than we ever dreamed. The signal from the atmosphere was just an invitation. The true mystery, the true wonder, lies beneath the waves of the hydrogen ocean. The discovery of a living world at K-18b was a thunderclap, a singular event that shattered the centuries of silence that had greeted our search for life. It was a moment that redrew the map of our cosmos, transforming a single, distant point of light into a place of profound significance, a beacon of biological possibility. But the true, world-altering implication of this discovery is not about a single planet. It is not about the specifics of its hydrogen ocean or the metabolism of its alien microbes. The true significance of K-18b is that it is a proof of concept. It is the first piece of empirical evidence that the universe we inhabit is not a sterile, empty void sparsely decorated with stars, but a fertile ground for biology. K-18b has opened the floodgates. It suggests that the miracle of life on Earth was not a miracle at all, but simply a local manifestation of a universal principle. And with this realization, our entire perception of the galaxy and our place within it must fundamentally change. For centuries, our scientific worldview has been shaped by the Copernican principle, the idea that we are not special, that Earth is not the center of the universe, that our position in space and time is not privileged. We have embraced this cosmic humility in our astronomy, our physics, and our cosmology. But in the realm of biology, we have secretly, perhaps subconsciously, clung to a sliver of exceptionalness. We have treated life on Earth as a near impossible accident, a chemical fluke of such staggering improbability that it was unlikely to have happened anywhere else. We spoke of the Goldilocks zone as a razor-thin edge of cosmic real estate, as a rare Earth hypothesis, which argued that the specific combination of a stable star, a large moon, plate tectonics, and a protective magnetic field made our world a singular miracle. KT-18b demolishes this last bastion of human exceptionalism. It presents us with a world that is, by all terrestrial standards, profoundly alien. It is a massive super-Earth, not a small rocky planet. It orbits a dim red dwarf, not a bright yellow sun. Its atmosphere is a thick blanket of hydrogen, not a thin veil of nitrogen and oxygen. And yet, not only does it appear to be habitable, it appears to be inhabited. This discovery does not just add one more date, a point to our census of worlds. It forces us to rewrite the very definition of a habitable world. It tells us that our Earth-centric template was too narrow, too limited, too lacking imagination. The universe, it seems, does not need to create a twin of Earth to create life. It has other, perhaps more common, and potentially more effective ways of doing so. With this new understanding, let us cast our eyes out into the galaxy once more. The Milky Way is a vast island of stars, home to an estimated 400 billion suns. For decades, our attempts to estimate the number of life-bearing worlds through thought experiments like the Drake equation were exercises in pure speculation. We had no data for the most crucial variable, the fraction of planets on which life actually arises. K-18b gives us our first data point, and it is a spectacular one. It suggests that the number is not zero, and if it is not zero here, in our immediate cosmic neighborhood, then it is unlikely to be zero anywhere else. Let us consider the numbers. The star K-18 is a red dwarf. Red dwarfs are, by a huge margin, the most common type of star in our galaxy, making up roughly 75% of the stellar population. Our Sun is an exception. Red dwarfs are the rule. Furthermore, recent surveys have shown that planets are incredibly common around these stars. It is estimated that, on average, every red dwarf in the galaxy hosts at least one planet, and many of those are small planets located within the star's habitable zone. Now, with K-18b, we have evidence that a significant fraction of these worlds might not just be rocky super-Earths, but high CE and planets with the thick hydrogen atmospheres and global oceans that seem to be so conducive to life. If we are conservative, if we assume that only a tiny fraction of these billions upon billions of planets in red dwarf systems are true high CE worlds, and that only a tiny fraction of those actually develop life, the numbers are still staggering. The result is not a handful of living worlds, but millions, perhaps billions. The Milky Way may not be a lonely desert with a single oasis. It may be a lush, vibrant, and sprawling cosmic garden with life sprouting in countless hidden corners. We are not just looking for a needle in a haystack. We are beginning to realize the entire haystack might be made of needles. This discovery also forces us to re-examine the famous Fermi paradox. If the galaxy is so vast and so old, and if life is common, then where is everybody? The discovery of abundant microbial-level life on a world like K-18b does not solve this paradox, but it deepens it in a fascinating way. It suggests that the emergence of life itself may not be the great filter. The universe seems to have no problem creating biospheres. Life, in its simple microbial form, may be a common and natural outcome of cosmic chemistry. This shifts the focus of the paradox. If simple life is common, then perhaps the true bottleneck, the great filter, lies further down the evolutionary path. Perhaps the transition from simple microbial life to complex, multicellular life is the incredibly rare event. On Earth, this transition took billions of years, perhaps on most worlds. Life remains a simple, microbial slime for its entire history, or perhaps the filter is the emergence of intelligence itself. Or, more sobering still, perhaps the filter is the development of a technological civilization that is capable of surviving its own adolescence without destroying itself. The silence we perceive in the cosmos might not be the silence of an empty galaxy, but the silence of a galaxy filled with thriving biospheres that have simply not produced civilizations capable of broadcasting their presence across the stars. But perhaps they are wise enough not to. The discovery on K-18b also hints at another profound possibility: cosmic convergent evolution. On Earth, we see this phenomenon everywhere. Unrelated species, in different parts of the world and at different times, have independently evolved similar solutions to similar problems. The eye has evolved independently dozens of times. Wings for powered flight have evolved in insects, pterosaurs, birds, and bats. It seems that physics and chemistry create a set of good solutions to the challenges of life, and evolution, through natural selection, tends to find them again and again. The detection of dimethyl sulfide on K-18b could be the first example of this principle on a galactic scale. The fact that a world 120 light-years away has a biosphere that utilizes a sulfur-based metabolism, producing the exact same complex biosignature molecule as life in Earth's oceans, is a stunning revelation. It suggests that the basic building blocks and metabolic pathways of life may not be as random as we once thought. Just as there are universal laws of physics that govern the formation of stars, there may be universal principles of biochemistry that guide the evolution of life. Carbon chemistry, liquid water as a solvent, and sulfur-based energy cycles might be the good solutions that life discovers again and again. Across countless worlds, we may find that the tree of life is not unique to Earth, but that there is a vast, galactic forest of life, and all its trees share a common set of foundational biochemical principles. The floodgates are now open. The search for extraterrestrial life has been transformed. It is no longer a speculative, fringe quest, but a systematic, evidence-based survey. We have moved from asking if life exists to asking where it exists and what kind of life it is. Every new exoplanet discovered by Webb and future telescopes will now be scrutinized with a new sense of purpose. We are no longer just cataloging worlds. We are assessing them for signs of habitation. We will build a library of atmospheres, comparing and contrasting the chemical fingerprints of dozens, then hundreds of worlds. We will look for more planets with the telltale signs of DMS, methane, and chemical disequilibrium. We will search for worlds with oxygen, the breath of photosynthetic life, and we will search for worlds with chemistry so strange they defy our current understanding. The discovery of K-18b has given us a new lens through which to view the cosmos. It has transformed the pinpricks of light in our night sky from distant, sterile objects into potential homes, potential biospheres, potential neighbors. It has taken the abstract, philosophical question of our loneliness and placed it firmly in the realm of observational science. The universe has revealed a secret, and in doing so, it has become an infinitely more interesting, more hopeful, and more awe-inspiring place. The silence has been broken, and we are beginning to realize that the galaxy is not an empty void, but a place filled with the quiet, persistent, and now detectable hum of life. We stand at the precipice of a new epoch. In the quiet hum of a server processing light from a world 120 light-years away, a line was drawn through the history of a species. Before this moment, we were a people defined by a question: are we alone? After this moment, we are a people defined by an answer: no. This knowledge, now as fundamental as the understanding that the Earth is round, or that it orbits the Sun, changes everything. It is not an incremental advance. It is a phase transition in human consciousness. The discovery of life on K-18b is not the end of the search, but the beginning of a new reality, the opening of the 10th, and perhaps most profound, chapter in our cosmic story. This is the story of what comes next. This is the story of humanity's cosmic future. The first and most immediate consequence of this discovery is psychological. For all of our recorded history, a sense of cosmic loneliness has been a silent, persistent undercurrent in the human spirit. It has haunted our philosophies, shaped our religions, and infused our art with a feeling of profound, but ultimately solitary existence. We were the universe's only known spectators, a brief spark of consciousness in an immeasurable, indifferent void. That era is over. The knowledge that we are not alone will end the existential solitude that has defined us. We are no longer an anomaly. We are part of a larger pattern, a member of a galactic community of living worlds. Every child born after this moment will grow up in a different universe than their ancestors. They will look up at the stars not as distant, cold points of light, but as potential homes, as neighbors. The constellations will be redrawn in their minds, not as mythical figures, but as a map of known biospheres. The question will shift from, is anyone out there, to what are they like? This change will ripple through every aspect of our civilization. Our science will be revolutionized as we grapple with the reality that biology is not a few unique to Earth, but a fundamental feature of the cosmos. Our philosophies will be transformed as we reconsider the nature of life, consciousness, and our own place in a universe that contains other forms of life. Our religions will have to contend with a creation that is far grander and more populated than their scriptures ever imagined. Our art will find new inspiration, new metaphors, new stories to tell about our relationship with a living universe. But this new chapter is not just one of philosophical reflection. It is one of intense, focused, and re-energized scientific exploration. The discovery of life on K-18b has given us the ultimate justification for pushing our technological boundaries further than ever before. The search for extraterrestrial life has been transformed from a speculative, fringe quest into a systematic, evidence-based survey. We have moved from asking if life exists to asking where else it exists and what kind of life it is. The next generation of great observatories is already being designed, and their mission is now clearer and more urgent than ever. Projects like the Habitable Worlds Observatory HWO, a space telescope conceived as a successor to Webb, will be designed specifically to take the next great leap, with mirrors even larger and more sophisticated than Webb's, and with chronograph technology capable of achieving contrast ratios of 10 billion to 1. These future telescopes will be able to do what was once considered impossible, to directly image Earth-like planets around Sun-like stars. This is the holy grail of exoplanet science. It means separating the faint, reflected light of a planet the size of Earth from the overwhelming glare of its parent star. It is like trying to spot a firefly next to a searchlight from thousands of miles away, but the firefly is 1 billion times fainter. Achieving this will allow us to analyze the atmospheres of these true Earth twins in unprecedented detail. We will no longer be limited to studying the atmospheres of transiting planets. We will be able to look at any nearby planet, regardless of its orbital inclination. We will build a library of atmospheres, comparing and contrasting the chemical fingerprints of dozens, then hundreds of worlds. We will look for more planets with the telltale signs of dimethyl sulfide, methane, and chemical disequilibrium, the signatures of a high CEN world biosphere. But we will also look for the specific biosignatures of a world like our own. We will search for the unmistakable fingerprint of abundant free oxygen, the waste product of photosynthesis on a global scale. We will look for ozone, a byproduct of oxygen that shields a planet from harmful ultraviolet radiation. We will search for the seasonal variations in carbon dioxide, the signature of a planet breathing with the rhythm of its seasons. As plant life blooms and decays, we will be able to tell if a planet has clouds, and perhaps even what those clouds are made of. We will be able to measure the glint of sunlight off a liquid surface, confirming the presence of oceans, and mapping the distribution of land and water. We will move from detecting biospheres to characterizing them. And this leads to the most tantalizing prospect of all. With these new capabilities, the search for extraterrestrial intelligence, or SETI, will transform from a passive, listening exercise into an active, observational science. For decades, SETI has relied on radio telescopes, hoping to eavesdrop on a deliberate, powerful transmission from another civilization. It was a search based on a huge number of assumptions about alien technology and motivations. But future telescopes will allow us to search for techno-signatures, the passive, unintentional evidence of a technological civilization written into the chemistry and physics of its homeworld. What would we look for? We would search for molecules in an atmosphere that have no natural source. On Earth, industrial processes produce compounds like chlorofluorocarbons CFCs, which are incredibly potent greenhouse gases and would be an unambiguous sign of technology to any distant observer. We could search for them on other worlds. We could look for large-scale structures in orbit around a planet. Things like massive solar collectors or artificial habitats, which would periodically block the starlight in a way that is distinctly non-natural. With direct imaging, we could even analyze the night side of a planet. While a natural world would be dark, a planet hosting a global civilization might have a faint, organized glow from its city lights. The search for intelligence will become a routine part of exoplanet characterization, a checklist item for every promising world we find. We will no longer be just listening for life, we will be actively looking for its handiwork. But this new power brings with it a new and profound responsibility. As we identify more and more living worlds, we will face immense ethical questions that have, until now, been the sole province of science fiction. We will have a catalogue of our living neighbors. What do we do with that knowledge? This is the prime directive problem, and it is no longer a fantasy. Do we have the right to make contact? A deliberate, powerful broadcast towards a world we know to be inhabited would be the most significant decision in human history. It would be an act of cosmic introduction, one with consequences that are completely unknowable. Would we be greeted with curiosity, indifference, or hostility? Would our message be a beacon of friendship, or a dinner bell announcing our presence to a more advanced and perhaps predatory civilization? Or do we have a moral obligation to remain silent, to observe these worlds from a distance, as cosmic anthropologists, protecting these nascent biospheres from any potential contamination from us? This contamination could be biological, a stray probe carrying terrestrial microbes that could wreak havoc on an alien ecosystem. But it could also be cultural. The mere knowledge of our existence could irrevocably alter the course of a developing civilization, a form of intellectual contamination from which they could never recover. We are no longer just explorers, we are potential guardians, and the weight of that responsibility is immense. These will be the great debates of the 21st and 22nd centuries, debates that will take place not just in scientific conferences, but in the halls of international government. The discovery of life on K218b, therefore, is not an end point. It is the starting gun for a new race, a new era of exploration that will define the future of our species. It has given us a roadmap, a set of chemical signposts to look for in our search. It has given us the political and social impetus to build the next generation of great observatories, and it has given us a new sense of our own identity. We are the generation that learned we are not alone. The silence we heard for so long was not the sound of emptiness. It was simply the sound of our own technological deafness. Now, for the first time, we are beginning to hear the music of a living universe. The future of humanity lies in the stars, not just as a destination for our spacecraft, but as the source of answers to our deepest questions. We will continue to look, to listen, and to learn. The story of K218b is just the first of many such stories we will uncover. The universe has revealed a secret, and in doing so, it has invited us to participate in a much grander narrative than we ever imagined. Our cosmic future is not one of solitude, but of discovery, of responsibility, and ultimately, of connection to a universe that is not just habitable, but abundantly, magnificently alive.